This is going to be a crash course in Game Boy assembly. If you're not sure why you should bother, then have a look at my other video. By the end of this video, you'll hopefully have a working Game Boy ROM that displays something like this. Beautiful, isn't it? You gotta start somewhere though. I'm not going to teach you everything about Game Boy assembly programming. Where'd be the fun in that? Here's what you will get from this video. An introduction to the required tools so that you'll know how to turn your assembly code into a Game Boy ROM. The basic paradigms of assembly programming so that you'll know how to orient yourself when looking at assembly code. Some specifics about the Game Boy that'll be helpful. A few assembly instructions. And an introduction to the Game Boy assembly instructions documentation so that you'll be able to keep learning on your own. Hopefully, by the end, you'll feel comfortable enough with Game Boy assembly and the documentation to continue your journey on your own. And if you've tried to learn to program before, but things didn't quite click for you, or maybe there are some tricky math topics that you'd love to genuinely understand, but you don't know how to get there on your own, then you should check out this video's sponsor, Brilliant. Brilliant helps you excel in math and computer science with visual, interactive problem solving and personalized practice. One thing I believe is that anyone can learn any topic with enough of the right resources, and that aligns with Brilliant's philosophy too. For example, they believe everyone is a math person. It's the way we learn math that can feel confusing and hard. With Brilliant, you don't just memorize formulas. You get hands-on with concepts until they make sense. Brilliant guides you to aha moments, helping you develop the intuition and problem-solving skills to figure things out on your own. And having the confidence to believe you can do that, figure things out on your own, is an amazing attribute. I never would have jumped into Game Boy hacking and programming without it. To learn for free on Brilliant, go to brilliant.org/systemoflevers. Scan the QR code on screen or click the link in the description. Brilliant will also give you 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. First thing, I'll need to tell you what software you'll need. This was included in the video about why you should learn Game Boy assembly, so skip to here if you've seen it or already know. You'll need an assembler toolchain. RGBDS is what I'm going to be using here, so you should probably use it too. You can install it on Linux, Mac, and Windows. In the previous video, I said you needed the Windows subsystem for Linux to install it on Windows. But I was wrong. You don't. It's just the recommended way if your version of Windows supports it. If you have trouble installing it or don't want to be bothered, you can try out the online version to get started. You'll also need an emulator with good debugging support. If you don't want to make your own, then I recommend BGB. It's Windows native, but runs fine on Linux and Mac using Wine. I've also used SameBoy before on Mac. And again, if you don't want to be bothered, there's an online option called Wasmboy. You could also use real hardware with a flash card, but iterating on your code is faster without the delay of loading the ROM onto the cartridge. It's also nice to have the debug features. And of course, you'll need an IDE or text editor to write the code. I use VS Code with the RGBDS Z80 extension. Now, onto that Game Boy assembly crash course I promised you. My goal here is to get you started and cover the basics. Some of the explanations are going to get a bit into the weeds, and I know you hang on my every precious word, so I want to tell you now. Most of the details aren't important to get started. I'm including them because, well, I like explaining things, I guess. I don't want you to get bogged down by them. The important thing is to get started writing some assembly. So if the details are getting in your way of getting going, feel encouraged to skip them. I've set up chapter markers so you can go straight to the important parts. We're going to be relying a lot on the RGBDS documentation, which includes a description of all the assembly instructions. We'll also need the pandocs, which is a detailed documentation of how the Game Boy works. The first thing you'll need to do is install RGBDS and an emulator, and get your text editor ready. If you're having trouble getting and installing those things, remember that there are web-based versions of them, so don't let it block you. If you want, you can always come back later to get your local development environment set up. What's important right now is to get going so that assembly programming can get its hooks into you so that you keep going, or to figure out you hate it and never want to do it again. You definitely want to figure that out quickly. You don't want to waste your time on something you hate. Of course, just having those programs doesn't do much. How do you use them? This is going to be one of those detailed explanation sections, so skip to here for a summary if you want. First, I want you to create an empty file called empty.asm. Now go to the command line and type rgbasm-o empty.o empty.asm. That command uses the RGBDS assembler to turn the assembly file into an object file, the -o specifying the output file name. An object file is part way to being the binary machine code that Game Boys can run. All the human-readable instructions have been turned into numeric opcodes, but there are still some details that need to be dealt with, like labels and code locations. Code location is based on sections. All the code you write needs to be in sections. A section is defined by writing section, name, comma, type. There can also be some options. The type tells you what type of memory to put it in. All these are for different types of RAM. They're for reserving space in RAM that your code will use while it's running, not for writing code in. These two are for ROM, and it's the stuff that'll end up in a ROM file or on the ROM chip of a cartridge. The 0 and X refer to memory banks. I'm not going to get into that in this video. ROM 0 is either the first 16K of ROM or the first 32K, depending on linker options. We're only going to use ROM 0, so we're limited to at most 32K ROM files. Everything in a ROM section will be together in the final ROM. But RGBASM doesn't choose where in the ROM it will be. That's where RGB link comes in. RGB link is a linker. It figures out where all the sections are going to go. Again, it's not doing much here since there's no assembly code. We run it like this: RGB link -o empty.gb empty.o. We're specifying the input object file and using the -o flag to give an output file name. You'd use the -t flag to allow ROM 0 to be 32K instead of 16K. The output file has the .gb extension to say it's a Game Boy ROM, which is sort of true. It is technically a ROM file, but it's missing some things. If you put it into a cartridge and tried to run it on a Game Boy, you'd get this. Remember when I said the Game Boy has virtually no copy or bootleg prevention? This is where the virtually comes in. The way Nintendo intended to stop unauthorized games and cartridges from being sold was through trademark enforcement. You know that logo that famously scrolls down the screen when you boot up a game? That's not coming from the Game Boy. It's coming from the cartridge. You can actually get it to say whatever you want, but the Game Boy will only play the game if it's the Nintendo logo. The theory being that if you want your game to run on a Game Boy, it needs to contain Nintendo's trademarked logo. That's real easy to circumvent. But if Nintendo didn't authorize you to use that trademark, then they could sue you for trademark infringement. Anyway, let's circumvent it. That's where RGB fix comes in. It adds the logo data to the right place in the ROM file. You can also do other important things, like set up the correct checksum values. The Game Boy also won't boot if the header checksum is wrong. You run it like this: RGB fix -v-o empty_fix.gb empty.gb. The -v flag is telling RGB fix to put in the logo and checksum, and the -o flag is saying the output file. You can tell it to output to empty.gb if you want, and it'll just overwrite it. You have a real working ROM that you can run on an actual Game Boy if you want. If you load it up in your emulator of choice, it will show the Nintendo logo, and that's it. Maybe it'll give you an error about an illegal opcode. To summarize, your assembly code is written in files with a .asm file extension. If your file is called input.asm, to turn it into a Game Boy ROM, you run the following command sequence. This gives us a Game Boy ROM called my_rom.gb. Now you know how to use your tools. Let's learn some assembly. In the next section, I'm going to go over some boilerplate code you'll need to write. It's another detailed explanation section, so again, skip to here for what you need to copy to just get going. We'll need a section to put our code. We'll call it header, which will make sense in a moment. The Game Boy starts executing ROM code at address $100. That's in hexadecimal, by the way. All the numbers starting with $signs are hexadecimal numbers here. Normally, the linker would place a section and its code wherever it wants, so we need to tell it to start this section at $100, like this. Remember the logo data that needs to be in every ROM? That needs to be at address $104. That only gives us 4 bytes to write our code. This is silly, but there are some technical reasons why it's like this. Anyway, the reason I had you call this section header is because in the ROM, from address $100 to $150 is reserved for the cartridge header, or ROM header. It has a bunch of data like the logo, checksums, and info about the cartridge. So the next safe address for our code is $150. So to make this all work, our first instruction will be a jump. A jump instruction tells the Game Boy to stop executing instructions here and go start executing them at some other address. It's written as JP, then the address. So let's write JP $150. Now we need to reserve the space for the rest of the header up to address $150. If you don't want the details, just write DS $150 minus @ comma 0 and skip to this timestamp. DS isn't an assembly instruction. It's an instruction to tell the assembler, RGBASM, to do something special. DS tells RGBASM to put some bytes repeated a certain number of times here in this section in the object file. In this case, it'll write the byte value 0, $150 minus @ times. The @ symbol is a special symbol that just means the current address. So this will put enough zeros to fill up from the current address to $150. Maybe this is all a bit confusing, so we're going to dig in a little bit to see what this is doing. First, we'll put another JP $150 right after the DS instruction. Now, save that file and assemble and link it, like this. But don't run gbfix on it. Now, if you open up that .gb file in a hex dumper or hex editor, we can see what's in it. This shows you all the bytes in the file. In my case, each line contains 16 bytes. On the left, it tells you how many bytes into the file each line is. That maps exactly to ROM addresses. The bytes up to address $100 are all 0. Then we have bytes C3 5001. That's our JP $150 instruction. The 5001 is the address 150 we wrote. It shows up here as 5001 because the Game Boy uses little endian byte order for multi-byte values. C3 is the opcode for this particular type of jump. After that is a bunch of zeros again. These are the zeros from the DS instruction we wrote. Then, at address $150, we see another C3 5001, which is the second JP $150. And it's a bunch of zeros till address 3FFF, giving us a 16 kilobyte file. If we had used the -T flag, it would go up to 7FFF. Now, if we run rgbfix-v-o infloop_fix.gb infloop.gb and look at that file, we can see it's mostly the same, except between address $104 and $133. That's the logo and checksum data that RGBFix added in. We can get rid of that second JP instruction now. Okay, to summarize, our starting file should look something like this. And we saw our first assembly instruction, the JP instruction that tells the CPU to jump to a specific memory address and start executing from there. We're not quite done with the boilerplate just yet, unfortunately. There's one more thing we need to take care of. We need to turn off the screen. This next part has a bunch of detailed explanation again, but I'm also going to be introducing some new instructions and concepts, so you probably shouldn't skip it. I'll give a summary of it at the end though, in case you decide not to listen to me. We're going to be changing some graphics, and that's a bit harder while the screen is on, because the video RAM can't be accessed while the Game Boy is actively rendering the screen. There are times when it isn't actively rendering, called H blank and V blank. But if you're going to be changing a lot of stuff in video RAM, and it's okay for the screen to be blank for a moment, then it's easier to just turn off the screen to give you full access to the video RAM. There's a catch though. You can't just turn off the screen whenever you want. Well, you can, but you risk damaging the display. So don't. You need to wait till the screen is finished being rendered. The Game Boy keeps track of what line of pixels are currently being rendered. We'll use that to wait until rendering is done. The Game Boy uses a memory mapped architecture. All the different parts of the Game Boy system are mapped to special memory addresses. In this case, the line number that's currently being rendered can be found at $FF44. This particular bit of info can be found in the Graphics LCD Status Registers section of the Pandocs. If you don't like using magic hex numbers in your code, there's a file on gbdev.io called hardware.inc that defines a bunch of constants to make your code more readable. If we were using it, we could use RLY instead of $FF44. I decided not to use it to avoid having one more bit of complexity though. The Game Boy screen has 144 lines, and the line counter starts at 0, and 143 is the last line. So when it's 144, we know rendering is done. So we just need to get the value at FF44 and check if it's equal to 144, looping until it is. To accomplish that monumental task, we're going to need two new instructions: a new type of jump, CPU registers, CPU flags, and labels. I'll talk about registers first. They're an important concept in assembly programming and CPU architecture. Registers are small bits of memory inside the CPU. CPUs generally don't work directly with the main memory. You have to load data into registers and do the work there. For example, if you want to add two numbers from memory and store the result back to memory, you'd first load the two numbers into registers, do the addition, storing the result in a register, then writing the value from that register to the desired memory location. The Game Boy has 7 general-purpose 8-bit registers. 6 of them can be paired off into 16-bit registers. A and HL are special registers. A is called the accumulator, and I've seen HL called the address register pair. I'll explain those more in a bit. There are 3 extra special registers: SP, PC, and F. SP is the stack pointer and relates to the function call stack. PC is the program counter. It's where the address of the next instruction is stored. When you use a jump instruction, you're modifying PC. F is the flag register. It has extra information about the last operation. We'll see what I mean in a moment. To make things a bit confusing, the special memory locations that interact with the Game Boy hardware, like the line number we're dealing with, are also called registers. Those are called I/O registers, so just know the difference, I guess. Okay, so we want to check if the value at $FF44 is equal to 144. First thing is to get the value from memory and put it into a register. We do that with a load instruction, written LD. LD is how we move data around in the Game Boy, and there's a bunch of versions of it, but they all do the same basic thing. They copy data from one place to another. We want to copy data from $FF44 and put it in register A. Now's a good time to have a look at the RGBDS documentation on CPU instructions, so we can figure out how to do that. These are the basic load instructions. There are some others related to the stack pointer further down that we'll ignore. This list tells us all the ways we can move data around, and it uses some abbreviations to do it. Anywhere you see an R8 can be replaced by an 8-bit register. Anywhere you see an N8 can be an 8-bit number. This load says you can write LDA, $2A, which means you can put the value $2A into the register A. R16 means 16-bit registers, and N16 means 16-bit numbers. There are a few other abbreviations listed above in the legend. Some of the versions of load have these square brackets. The square brackets mean treat what's in them as a memory address, and load to or from that address. You'll also see specific registers being used, like A, HL, and C. When you see that, it means you have to use those registers for that type of load. You might also have noticed HLI and HLD. Those are special, and we'll get to them in a bit. There's also LDH. Those are faster loads that can only access memory in the $FF00 to $FFFF range, called high RAM. We want to load a value from memory using a 16-bit address into an 8-bit register. There's no load instruction that lets you load from an N16 address into an arbitrary R8, but there are these two that let you load from an N16 address into A. That's one way A is special. There are certain load instructions where you can't use other registers. We can use the LD or LDH version. It doesn't make a huge difference here, but LDH is faster, so I guess use that. So, to load the line counter into a register, we write LD or LDH, A, square bracket, $FF44, square bracket. And now you have some idea of how to read the assembly instruction documentation. If you click an instruction, it will bring you to a description of what it does. Okay, now we need to check if A is equal to 144. We'll use the compare instruction for that, written CP. It's used to compare one value to the value in A. We'll use the N8 version. Let's go to the description to see what it does. It compares the value in A with the value N8. It does that by subtracting the value N8 from A, and sets flags accordingly, but discards the result. That's going to need some explaining. We have three cases. N8 is bigger than A, N8 is equal to A, and N8 is smaller than A. In the bigger case, A minus N8 will give a negative number. In the equal case, we'd get 0. In the smaller case, we get a positive number. We don't actually need to know the result of the subtraction, just if it's negative, 0, or positive. That's where the flags come in. They capture extra information about the last operation. The Game Boy has 4 flags. The Z flag that says the result of the last operation was 0. The N and H flags that relate to binary encoded decimal or BCD. I'm not going to talk about BCD. The last one is the C flag that tells you when there was a carry. That flag is set when a result is too big or too small. If we look at the description of CP A, R8, we can see what it does to the flags. Z will be set if the result is 0, and an H will ignore. C if there's a borrow, which is when R8, or in our case N8, is bigger than A. So if C is set, we know we're in the bigger case. If Z is set, we know we're in the equal case. Otherwise, it's the smaller case. We're trying to see if A is equal to 144, so we'll look at the Z flag. To check it, we're going to use the conditional jump. Conditional jumps are like an if statement, but worse. They have a condition, and if that condition is true, then the Game Boy jumps to the given address. If it's false, it just goes on to the next instruction. The conditions are limited to checking if a single flag is set. I said before, we want to loop until the line counter equals 144. So if the Z flag isn't set, we want to jump back here to do all this again. We write that as JP NZ, N16, where N16 is whatever the address of the start of this code is. We actually know that address. It's $150. But in general, it wouldn't be that obvious. We could figure out how many bytes away a given jump target is by looking up how many bytes each instruction uses, then adding or subtracting from the @ symbol. But that would break if you ever add or remove code. Plus, it doesn't work if you want to jump to code in a different section. That's where labels come in. In fact, we should have used a label instead of $150 up there. We'll put a label down here called my code, with a colon at the end. And up here, we replace $150 with my code. Now, we don't have a magic number in our code. The colon at the end of the label and the lack of period in it means it's a global label. You can also have local labels. This video is getting long, so I'm not going to explain it. You can read about labels in the RGBDS assembly syntax docs. The my code label also happens to be where we need to jump in order to loop. To summarize, we wanted to repeatedly check the line counter as long as it's not equal to 144. We check the line counter by loading its value from its memory address into the A register. We compare 144 to the A register, which sets flags based on how they compare. We use a conditional jump with the not zero condition to check that the zero flag wasn't set by CP, meaning A doesn't equal 144. If NZ is true, we jump up to the my code label to try again. If NZ isn't true, meaning A does equal 144, we'll continue on here to do the next steps. Now we can safely turn off the display. That's pretty easy. We just have to write the value 0 to the LCD control register at address $FF40, which is called RLCDC in the hardware.inc file. Remember, that's an I/O register, not a CPU register. If you want to write the code to do that yourself, you should pause here. Okay, we'll load a 0 into A. Then we'll load A to $FF40. It seems that people think LDA,0 is too boring though. So if there's a place where A needs to be set to 0, you'll often see XOR A. That's a shorthand for XOR A, A. The shorthand works because all 2 operand, 8-bit arithmetic, and bitwise operations must have A on the left side, and they all put the result into A. It's like A is accumulating the result, which is why it's called the accumulator. So because the left operand is always A, you can just omit it from the instruction. XOR is the bitwise exclusive OR. Each bit in A is XORed with the corresponding bit in the other value. XORing 2 bits that are the same gives a 0. So XORing A with itself makes A 0. People use XOR A instead of LDA, 0 because the machine code for XOR A is only 1 byte and only takes 1 CPU cycle to execute. And LDA 0 is 2 bytes and takes 2 cycles. Anyway, now you basically understand all the arithmetic and bitwise instructions. You just need to read their descriptions for more details, and to see how the flags get changed. Next, we're going to make some graphics. I'm not going to go into details about how Game Boy graphics work. If you want to know, you can check out the graphics section in the Pandocs, or watch my videos about Game Boy graphics. First thing I want to do is set the background palette to the normal value. The palette is set by the I/O register at $FF47, and you should set it to the binary value %11100100. That makes it so each pixel value maps to its equal color value. We're going to do something here, but after that, we just need to turn the screen back on with the right settings and enter an infinite loop. If you're curious about what that binary number means, have a look at the LCD control register documentation in the Pandocs. Next, we're going to make our own tile, so we'll need some tile data. Come down to the bottom of the file and add a local label called .tiledata. Now we'll hard code the tile into the ROM right here. The Game Boy's tile data format is kind of inconvenient for writing by hand, but RGBDS gives us a handy way to do it easily with the backquote prefix. It lets us write out our graphics data as pixel values. So we'll use the DW data definition command to make 8 lines of 8 pixels. You can make it whatever you want. Okay, back up to here. We need to copy that tile data into video RAM. I'll have you put it at the first tile at $8000. You actually have enough information now to figure out how to do that. You need to learn a bit on your own, but you don't need any new concepts. So if you want a challenge, try it now and see if you get it. We have 2 options. We could do a bunch of LD commands to copy the data, or we could use a loop. Let's use a loop. It's basically going to be a for loop. First, we need to set up some starting values. We'll set HL to $8000. That's our destination starting address. BC to the .tiledata label. That's our source starting address. And D to 16. That's our iteration counter. It's 16 because a tile is 8 lines and each line is 2 bytes. We'll need a label to jump to. Call it .copyLoop. Now we just need to load from BC into A and increment BC. Then load from A into HL. We'll use the HLI variant though. It works the same as LD HLA, except after the load is done, it increments HL. The HLD version decrements. Next, we'll decrement D and check if it became 0. If not, we jump back up to the start of the loop. If it is, we continue on to turn the screen back on and be done. Now assemble, link, fix, and try it out in your emulator. It should look something like this. Congratulations! You're a Game Boy assembly programmer now. The rest is reading docs, solving problems, and doing it a lot to get experience. I didn't cover some big topics though, like function calls and interrupts. But this video is getting too long as it is. You'll have to learn the rest on your own. If you want me to make a video covering it, then let me know in the comments. If you want somewhere to go from here, you could try making a game or game-like thing. Start really simple though, like tic-tac-toe maybe, or just moving a tile or sprite around on the screen. I hope you have lots of fun with this. Bye! I guess that's it.